Hi, today on Shelley Physics, I'm going to take you through 4 examples to apply F equals IL cross B. That's current through a conductor in a magnetic field. So our first one is sort of a repeat from the last episode. If we have a couple of conducting bars and put a cross bar right there with a positive and a negative charge, let's say the battery hooked up to this. Right there and right there, okay? Get those positive and negative sides. And we're going to add in a magnetic field. We're going to take one going into the page here. There we are. And if you do have your marker, please color that yellow as we do on Shelley Physics. I am unfortunately without my highlighter. So our current will be flowing from positive to negative. It'll flow up across this conducting bar and back along here. So the big question is, what is the amount of force on this middle bar? So I'm going to give some value to the magnetic field. So here's the magnetic field magnitude or intensity. The current I'm going to define as 5 amperes. Okay, and therefore, when we take F equals IL cross B, let's first consider that the length L across here crossed with B is going to give us a 90-degree angle. So we can just consider this F equals ILB, or F equals Bill, if you like that one. The length of a cross beam, I'm going to give it, that's the last little piece I need here. I'm going to make that 4 centimeters. All right. So to solve for that magnetic force on the bar, at least the magnitude, we'll come up with the direction in just a moment, is going to be the current, 5 amperes, times the length, 0.04 meters, it's 4 centimeters, times the magnetic field, 0.5. All right. So we have half of 0.04, and that gives us 0.02 times 5, and that gives us 1/10 of a Newton. There it is. So which direction will it be in? We have the current flowing up the bar. So in this direction, we're going to make our palm face toward the direction of the magnetic field, curve our fingers that way. Therefore, the force is going to be in the direction of my thumb to the left. Now we have the magnitude and direction of that force. We have the force vector. That's our example 1. Application number 2. All right, we're going to make this a little bit more fun. I'm going to start with a magnetic field coming out of the page on this one. Nice big picture. And in this example, I'm going to have a couple of different segments of conductor. Part of the conductor is going to be horizontal across the page, and right in the middle, I'm going to bow it up and give it a semicircular shape here. Getting fancy. There it is. Help if Shelley puts it on the screen. All right. Now, so we have a magnetic field going into the page. I'm not going to bother giving these values. We're just going to use some variables here. I'm going to call this from here to here length big L, and also another one over here length big L. Okay? L and L. There we are. And now in the middle, like I said, this is going to be a semicircle, so I'm going to call this radius R. I could go ahead and say that R is equal to, we'll go a half L, so L over 2. Let's keep that in mind, a relationship between the two. And let's see, what else do we need here? So I did define this as a semicircle, so half a circle is what I'm calling that. All right, I think that's all we really need here. So there are 3 different parts to this construction. there's a segment here, a length, got a length here, and this one. Now, these two lengths are of equal length, and they're going to be immersed in the same amount of magnetic field. I should define the direction of current here. Let's have the current going that way. I knew I was forgetting something. All right, so how much force will be on each of these segments? We would just have, since the current is perpendicular to the magnetic field, current flows to the right, magnetic field is up. So that means we're going to have a right flowing current. My palm is facing the direction of the magnetic field. So that's going to be a downward force. Hopefully you got that. We have a downward force here and also another downward force here. And we'll call that ILB. So there's just two ILBs on this segment of conductor. All right. We're going to go for the total force now. So now we need to look at the force on this little semicircle here. Now if I look at just a little piece, a little segment of that conductor, there's going to be a force dF from that little piece. And it has a length dl. So there's a tiny little bit of length in there and a tiny bit of force applied. The total force is going to be the sum of all the force on that segment. Now if we look at that, if the current is flowing in, I'm going to turn this a little bit, we have the current flowing in this direction with the field upward, then you'll see that that force is at an angle, and that force is always going to be towards the center. Okay, the force from this segment is going to be towards the center of that semicircle. Even over here. Pause this video now if you want to and do the right hand rule, and you'll find that the force on this little dF is also towards the center. So what we need to do is sum up all that force, find the sum of the forces. Well, if since we have F equals I L cross B, but that L cross B is magnitude LB, because the magnetic field is perpendicular to the current at all times. Even though the current direction or the L direction is changing as we go along here, it is always perpendicular to the magnetic field. So we don't have to worry about that, the sign of the component there. So we have F equals IL cross B, but we're looking for a small piece of that, small dF. The I, the charge per second through each segment, still remains constant. It's a ratio of charge to time. It's the rate of charge, so that's going to be constant throughout. The magnetic field is also going to be constant, but the length L that goes along with dF is actually length dL. So in a semicircle, how can we relate the tiny bit of length to the properties of that semicircle? Well, the semicircle has a radius capital R. My apologies. So we have dF equals IB dL. That semicircle has a radius capital R, and since it is part of a circle, we can look at the definition of arc length. S equals R theta generically. But now in our situation here, the little piece of arc length corresponds to dl, the length. Right? So I'm going to call this, instead of S, I'm going to call L. And instead of R, I'm going to use capital R, because that's a constant here. So what exactly is dl in terms of the properties of the semicircle? Well, if we take the derivative of both sides here, dl with a constant R will refer to a certain small bit of, go between here and here, there's that small little tiny bit of an angle d theta. So now we have the dF, the little small piece of force, infinitesimally small piece of force, in terms of a very small change in angle. All right, so rewriting this, dF equals IB R. Looks like I have a little extra d in there. Shirley's going crazy. All right, so R d theta. Okay. Now we can't integrate just yet because the direction of this force is changing. It has x components and y components. Now, if the force is always pointing towards the center, what can we say about the x component of the force, the net force due to the x components, if we add them all up, those little df's? Well, on this side, the little segment here will be pointing down and right, and the little segment over here that's at about the same angle is pointing down and left with the same magnitude but opposite x direction. So you might see here, if we sum up all these little df's, the x components will cancel. So I could say, by symmetry, the x components of the force cancel. It's a great statement, and you can probably move on from there. But you know, this is Shelley physics, so we're going to do it. It's not actually that difficult. So if we look at get some dimension here, if we look at a little theta right in here, and we're going to this segment here, it makes a triangle. The side of that triangle that's adjacent to the angle is the cosine component. So the x component is the cosine, and the y component is the sine. So I'm going to translate this up a little bit, translate my paper. If we look at the x components of the force, this will be I BR cosine theta d theta. And also we're going to have the y component being the sine. And we'll do both of these. Okay. So now we're ready to integrate. We're going from, we're summing up all the force. So this will be the sum of all the little pieces of F is F. And this will be in the x direction. There we go. Now there are upper and lower bounds here. We're going to be summing up all the little pieces df from 0 degrees up to pi radians. I should say 0 radians up to pi radians. So our angle is going to go from 0 to pi radians. All right, there it is. Now when we integrate that, what's the integral of cosine? That is our sine. Okay, so I BR sine theta, and we're going to go from 0 to pi. And here we're going to see if we plug in sine of pi minus sine of 0, we get 0. So that sum of all the forces in the x direction, we can say, all those little pieces, is 0. All right, so that net force in the x direction is 0. How about the net force in the y direction? We're going to sum all that up, and we're also going to go from 0 to pi. All right, and so this will be our y force, sum of all the forces in the y direction. And we're going to have an IBR, and the integral of sine theta is negative cosine theta. We take that from 0 to pi. So we got a negative IBR, and cosine of pi is -1. And then we subtract cosine of 0, which is 1. So we end up with a positive 2IBR. Getting my B and R's mixed up there. All right, so now we finally have a solution to this that we can bring together. What is the net force on this whole entire segment? We got an ILB downward, we got an ILB downward. Oh, we didn't figure out the direction of this. Now, oh yes we did. The y component of these forces are down and either left or right, but the x components canceled, so we only have a net downward force. So I should add that little bit there. This is going to be downward. All right, so our net force on the whole segment is 2 ILBs from those two side segments plus 2 IBR. But remember, I made a little definition up here. R is length over 2. So each R is L over 2. Therefore, I'm going to just substitute that in. IB, and the R there is L over 2. All right, so that 2 cancels, and I have 2I, that's a B. 2 ILBs plus 1 ILB is 3 ILBs. All right, so that's our application number 2. Moving on. Less math to do on this one. Application number 3. Do I have this zoomed in too much? I probably do. Anyhow, application number 3. What if we've got a little current loop? That's a circle. Nice perfect circle. And these wires come together real close together. So this is essentially an ugly circle, but it's supposed to be a circle. Okay, folks, just go with it. It's a circle. Okay. Stop hating on me. All right. Here we go. So we have our current coming in from the positive and flowing around. What do you suppose the net force is going to be on this loop? 0, because I've added no magnetic field, but actually it might also be 0 as well. So I'm going to put a magnetic field in here. It would be 0 force if there's 0 magnetic field anyway. There's our magnetic field. All right. So let's just look at this first segment of the wire. The current would be coming in, flowing in this direction. That's the direction of L. And the magnetic field is down. So I'm turning my palm downward and curling it that way. So as you can see, my thumb is pointing out this way. That's the direction of the force. Along the top, likewise, that arrow would be up like that. How about over here? That arrow would be out, kind of up and to the right. On the side over here, directly to the right. And as you might be able to imagine, continue that right-hand roll all around that loop. We're going to have an equal amount of force that is perpendicular to the wire at every single point. So the net force on this loop is 0 newtons. Okay, it balances itself out. Now structurally, what's happening here? This loop is pulling outward. So if we made many loops and put a whole lot of current through it, structurally this thing is going to have to stay intact. It's going to be pressured to be pushed outward. Or what happens if we flip the polarity here? Then our forces would be all pointing inward. Still a 0 net force, but this thing would have a kind of a crushing tendency. It would crush together. Okay. So that does happen structurally when we're dealing with these coil applications. And if you ever engineer one of those, that's something you have to look out for and just think about. All right. Application number 4. What about something like a motor, like a current loop? What if we have one of these loops? In my torque on a current loop video, I present a loop just like this. It's many loops together, and talk about how the torque is applied to different parts of this loop. So I'm going to try to sketch a few diagrams that go along with that. And this, with this loop, electricity is brought up through the paper clip, goes into the loop, circles around, comes down the other side. So that's the kind of scenarios we've got here. Let me start with a magnetic field going down the page here and try to draw in this loop, kind of see it from the side, goes off this way and comes around this way. Okay, so this loop is, from our perspective, coming out of the page. And I'm going to send in a current in this direction. So the current's coming this way and going out that way. You'll zoom in a little bit here. Okay. So what is the direction of the force on all the parts of the loop here? So the current's coming kind of out of the page here. We've got the current flowing out of the page towards us. Whoa, big hand. And the magnetic field is down, so that you do the right hand rule, please. You're going to find that there's going to be an outward force on that segment of the wire there. As the current flows around and over here, now it's going into the page on this side, into the page. That's the direction of the velocity. If the velocity is into the page down there and the magnetic field's down, then the force is going to be out to the left. So likewise, the force is always pointing outward. And here, the torque is 0. The net torque on all parts of that loop is 0. This is the axis of rotation, and none of those forces are perpendicular to that axis of rotation. So there's 0 torque. Remember, torque is R cross F, where R is there it is. R is the torque arm. That's the length is from the axis of rotation out to where the force is being applied. All right, so our next situation, we're going to rotate that a little bit. Okay, we're going to have a magnetic field down also. Going to keep that magnetic field consistent. But now I'm going to rotate this a little bit. There it is. Going to keep the current flowing in the same way and out the same way. And here's our horizontal plane. So the loop is now rotated kind of upward from that plane at an angle. Now the force is still going to be applied to the right. If you use the right hand rule, the force on this piece, this segment, is to the right, and the force on this segment is to the left. But now if you look at it, there is an angle between R and F. So there is going to be a torque value between R and F. There's R, there's F. Since there is an angle there, then there is a perpendicular component of F to R. So there is going to be a torque. Which way will this, if I force this loop to rotate from the horizontal position up to this position, there is going to be a clockwise torque about that center. It's going to rotate this way. This loop is being pulled to the left. This piece of the loop is being pulled to the right. It's a little more obvious to see if we look at it from this perspective. If we have the loop oriented so that the loop itself is in the same direction as the magnetic field. Here's our horizontal reference. So now we have that the wires coming in. But now we're going to have a loop. This one's the hardest for me to draw, so I'm pretty bad at it. Okay. There's our eye coming in and eye going out. So now with the eye coming in, at this point, we still have the current coming out of the page, so the velocity is up and out, facing my palm towards me. So by the right-hand rule, this part of the loop is going to the right, being forced to the right. And this part of the loop going into the page is being forced to the left. So here we've got maximum torque. I hope that's easiest to see. The torque, the R cross F, those two vectors are perpendicular to each other. So the sine of 90 degrees gives us the maximum out of that sine theta. The AB equals AB sine theta for the definition of the cross product. A cross B equals AB sine theta. So they are perpendicular to one another. So here the torque is maximum. The torque would be R cross F, which is RF sine theta. So for a magnitude, theta is a 90-degree angle, or pi over 2 radian angle. The r would be whatever radius that loop is, and the f is the velocity is coming out, the b is going down, so they're perpendicular. So F is the magnetic force on the wire. So that is ILB. So at this little piece here, whatever length that might be, we'll just call it L. Let's call a little segment L here, and ILB. So we get to do a little torque there. The torque would be R times ILB. We got a magnitude of the torque. And since this does relate to sine theta, when that angle is 90 degrees, we're going to have a maximum. When that angle is 0, we're going to have a minimum, a 0 torque. So the problem with the calculation for this circular loop is that we had to really look at, I kind of fudged it here with this, said this big L being a little segment down here. This loop is going to be a lot easier to look at if we consider it as a square loop. So if I draw this again, or attempt drawing number 2 here, of a square loop, and it could be a rectangular loop actually. I'm going to use sides A and B. Okay, we'll use these two sides are of length B, and we'll say these are of length A. So this is also B down here. All right, then the torque equals the magnetic force times the torque arm. Now the torque arm through the axis of rotation here is half of A. So this would be A over 2. That would be the torque. So now I just need to fill in what the magnetic force is going to be. That's going to be, you know, the magnetic field. Again, we have our magnetic field going down through here. So that's B. Times the current. Times the length. Now the length along each side here and here, with our forces going out that way and that way. Defined forces. The length of each of those segments is B. All right, so we got B, the magnetic field times the current times B. Now that would be the magnetic force on one of those segments. So keep in mind that there are 2 segments altogether. Now that all would be the net magnetic force on those 2 segments of the current loop, causing the current loop to rotate in torque. So we're going to multiply by the torque arm, A over 2, and the result there being BI, the 2's canceled, so we get A times B. Now if you look at that, A times B, what is that? That's the area of that loop. That's the area. So we might also say that the torque is the magnetic field times the current times the area. Now it's easier to translate that up to this current loop. We take the area within that loop, that might more approximate the torque on the loop.